Hello everyone, welcome to this class where we'll be doing exercises 418 and 420. And what are these exercises? These exercises are often referred to as the traveling salesman problem. The objective is to find the shortest route between a set of points and locations that must be visited, however, only once. The salesman goal is to keep both the travel costs and the distance traveled as low as possible. In the simple version, we'll have only one vehicle and one depot, and we must not forget that the salesman must start and must end each tour in the depot. To solve this problem, we want to create a mathematical model representative of our little supply chain. We can quickly identify what is going to be the decision. We want to know the route of the salesman. We want to know what is the location he is visiting first, and then from that one to the other. For that, we can use a binary variable denoting 1 if the arc between location I and j is used in the route, or 0 otherwise. The objective function comes as no surprise as the minimization of costs. How can we do that? We multiply the cost of each arc by the binary variable. That way, every arc en route will sum for the total expenses. We know that each location must be visited only once. That means that we have to implement constraints to limit that only one flow arrives at each client, and also that only one flow leaves each location. Here, we have all the flows possible for an example with 5 locations. And here, we have a feasible solution to our problem. And here, is this okay? It seems not. However, it fulfills all the restrictions we defined earlier. And these are examples of subtours, where a solution does not provide a continuous route. And that is something that we have to deal with. Dealing with subtours is rather challenging. From the possible methods, we'll be discussing these two. Miller, Tucker, and Zemlin, also referred as MTZ, and Danzig, Fulkerson, and Johnson, also referred as Danzig. We'll discuss them and implement them in our exercises so we can have a hands-on perspective. Recalling what you have already discussed in theoretical classes, we have the MTZ formula. Ui minus uj plus n times xijq lower or equal than n minus 1, not forgetting that I must be different than j and must be between 1 and n. Now, what do these letters represent? Ui is an integer variable that is going to represent the position of the stop in the route. That means if the client is the first, second, or third stop. N is the size of the set of locations, and xijq represents the binary variable related to the flow occurring or not. And you must not forget how are you going to write this in GUMS, and you must follow through with that notation that you used. So let's tackle the GUMS challenge. There are some things that we already used in previous exercises and some that might be new. We already know how to implement conditions in GUMS, and we do that with the $sign. We also want to avoid I and j from being equal, and we can do that in two ways, or with the symbols or with ne. One function that we will often use is the alias. This allows for the creation of several sets identical between them. In this case, I and j are locations from the same set, so we will say that I and j are alias. Now, let's implement the MTZ equation step by step. First, we want to name our equation. Then, we want to identify the dependent variables. In this case, we have no sums, and I and j are going to be here. We have also constraints related to them, so we have to write them here. First, we want to say that I and j must be higher than 1, and we also wish to say that I and j must be different between them. Only then we have the equation itself, where the only novelty is that we can represent n by using card I. Card I will return the size of set I. The Danzig approach is different to the MTZ. It will provide one equation for each size of subtours we want to avoid, so it might end up with a lot of equations. The equation itself is given by the double sum of the flows must be lower or equal than S minus 1, and S stands for the size of the subtour we are dealing with. If we want to implement the Danzig approach, how are we going to do it? Let's assume that we have a problem with 6 locations, so we want to avoid every subtour size until 5, because 6 is a complete route. We will create a lot of alias, since it is one for each element in the subtour. Let's see how we are going to implement in games. The smaller Danzig equation, S equal to 2. So the first thing we have to do is to name the equation and define the variables. Don't forget that the first element is the depot, so it has to be removed. The equation itself is simple, just the sum between x written so that it forms a loop. In this case, we say that the flow from P to R plus the flow from R to P has to be lower than S minus 1, being S equal to 2. If S is equal to 4, then we have a more extended equation, but in the same line with the previous. We have to create 4 aliases, and then don't forget to sum the flows so that they form a loop. And now we have a different exercise. We have 420. 420 will just present MTZ and hope that you find it interesting enough to do the Danzig on your own. The basis of the model you are expected to understand, okay, because it's pretty similar to what we have been doing in 3.4, 3.5 and 3.6. But just to recap, we have sets, parameters, scalars. You have to calculate the distances and also the variables. Now, the only thing that changes is that we have variables from the problem itself that you already know, and also you must not forget the variables from the MTZ formulation. So what is the difference between 420 and 418? We must not forget that most of these problems are somehow typified. In this case, we have a MILP model for a problem with a single depot and several vehicles. You can get more information in the study materials or in class 4.4 slide 28. The equations here are the most commonly used to model problems like the one in this exercise. You are expected to be able to understand and read the equations by themselves. You can ask yourself, this equation is constraining what? How many explicit equations in the context of this exercise does this equation stand for? So, let's try to group them. 1 and 2, what do you think? Can you guess? They are responsible for only allowing a flow arriving and leaving each node. And equation 3, can you suspect what the objective of this one is? It ensures that the continuity of the flows for a given route, so it doesn't change the route in the middle. Equation 4 is rather trivial. It just preserves the track capacity. Finally, equations 5 and 6 ensure that every route must contain the depot. As this only works if you put your hands on, don't forget to do the Phoenix worksheets. They are the most powerful tool for you to get feedback on your work, allowing for errors to be identified, and if a solution is not found, to take full advantage from the time with professors, not wasting time with what you could have done it alone. Good work!